Okay, we now investigate properties of orthonormal sets. So we start with the following proposition. Let H Hilbert space and E1 to En a finite orthonormal set in H. Let X belong to H, then sigma I equals 1 to n mod x ei square is less than or equal to norm x square. Further, x minus sigma I equals 1 to n x ei is orthogonal to each ei 1 less than or equal to each ej, let me say 1 less than or equal to j less than or equal to n. Okay, so proof. This is fairly straightforward. So you have that 0 is less than or equal to norm of x minus sigma I equals 1 to n x ei whole square. So let us develop this. So this is equal to norm x square plus sigma I equals 1 to n mod x ei square, norm ei square, that is 1, then minus 2 sigma I equals 1 to n. So these are all the cross terms, x ei, so that is mod x ei square. Then the other cross terms will involve ei inner product ej, but that will be 0 because if I is not equal to j, and consequently they will all not appear. So this is equal to norm x square minus sigma mod x ei square I equals 1 to n, and that is exactly this relationship. Now if you take x minus sigma x ei I equals 1 to n, and then take its inner product with ej, then this will be equal to x ej minus, now by linearity every ei ej will get killed because that's 0, and only ej will survive, so that is equal to minus x ej is 1, and therefore that is 0. And that proves you the second part of the proposition, namely that every this element is orthogonal to every ej. Okay, so next is an important proposition. Okay, so H Hilbert space and I indexing set. And let ei I in I be an orthonormal set in H. Then so let x belong to H, then define S equals set of all I in I such that x ei is not 0. So let me not put it then here, so let's say define, then S is at most countable. So proof, only need to consider the case when I is uncountable. So if I is finite, empty, finite or countable, there is nothing to do. S will automatically be countable at most, and therefore we need not worry about it. So we only case thing. Now define Sn is set of all I in I such that mod xei square is strictly bigger than norm x square over n. Then by the previous proposition, you have that norm x square dominates sigma I equals 1 to n xei square. So if each one of them is bigger than 1 by n, how many can there be? So then by previous proposition, Sn has at most n minus 1 elements. This implies S, which is equal to union n equals 1 to infinity Sn, is countable. Okay, so that proves that thing. So now this is very important, though it's a very simple proposition. It's a very important proposition because it tells you how to define. So to define sigma I in I mod xei square. Okay, so we want to define this particular sum. Okay, if S is empty, if I is empty, you put, so sum is 0. If I is finite, then sum is the usual sum, because it's a finite number, so you don't have to know. So I is infinite, then sigma I in I mod xei square is nothing but sigma I in S mod xei square, which is a countable set. So you take a numbering. So let us consider a numbering S equals E1, E2, En and so on, and then we define x I in I xei square. By definition, this is sigma I n equals 1 to infinity mod xen square, and that's an infinite series which you know how to define. It's the limit of the partial sums. Okay, and then since the terms are all greater or equal to 0, in fact strictly 0, the numbering is unimportant. Because if you take a series of non-negative terms, then any rearrangement will give you the same sum. If it's one of them is divergent, all of them will diverge. If one of them converges, they will all converge to the same sum. Okay, this is a famous theorem in infinite series, and therefore when you have a non-negative series, then it doesn't matter how you number these. You can number them in any way and it doesn't matter. And that's very important also, because we should not worry about how we have to do it. Okay, so now we can generalize the proposition which we proved earlier. So again you have theorem, and this is called Bessel's inequality. So H Hilbert space, let EI I in I be an orthonormal set. So let X belong to H, then the Bessel's inequality says that sigma I in I mod xei square is less than or equal to norm x square. So proof, if S is empty, nothing to prove. The sum is 0 and therefore 0 is less than norm x square. This is a triviality. If S is finite, already proved. So S is countable, that's the only third possibility, the countable, because that's how you define the infinite sum, and then already proved for partial sums, because that's the finite case which we have done, hence star is true. So this is true, and therefore we have proved Bessel's inequality completely. Now we are going to do something a little more ambitious. So H Hilbert space, and then EI I in I orthonormal set in H. So we want to give, and X is in H. So to give a meaning to sigma I in I X EI EI. Okay. So how are we going to define this particular thing? Again, if S is empty, so call this capital X. Okay. So where capital X belongs to H, we want to define it as a vector in H. So this infinite series should be defined. So then capital X equal to 0. Okay. If S is finite, then capital X equals usual vector addition. So the third possibility is when S is countable. So let us write S equals E1, En and so on. Okay, and then let us take Yn equal to sigma I equals 1 to n x ei ei, which is well defined, no problem. So now let us look at Yn minus Ym norm square. So let us say n is bigger than m. So this is equal to sigma I equals m plus 1 to n mod x ei square. Okay, this, because the all other things get cancelled. Okay, so if you do this, now this can be made arbitrarily small. For nm large. Why? Because sigma of mod x ei square is a convergent series by Bessel's inequality. This is finite. So this is part of the tail of a convergent series, and therefore the Cauchy criterion tells you can make this. So this implies that Yn is Cauchy and H is complete, and therefore Yn converges to some y, and we define y equals sigma I in I x ei ei. Okay, so we have done this, but then we have to be careful, because now we have to really check. If you number the vectors in a different way, then you may get a different vector. So that we should not, that will be an unpleasant thing to happen, and therefore we must avoid that. So let us So let us, okay, so this is not, so let us take E to be the set of the EI. S is a set of all I such that XEI is not 0. So S is a subset of the indexing set. So I want this here. So now let us say we have renumbered E. So let us say E is now written as some E1 dash, E2 dash, En dash, etc. So each Ei dash equals Ej for some j, and vice versa. So it's the same set which we have renumbered, and therefore we call them E1 dash, E2 dash, En dash, because it's written in a different order. It's the same set as original set. So now again, if you write Y dash, you can define as sigma I equals 1. So this is nothing but sigma n equals 1 to infinity x en en. Okay, so this is the definition of y. Okay, so now if you take I equals 1 to infinity x ei dash, so to show y is the same as y dash, so that once again we are in the clear. We can number the vectors in a countable set of vectors in any way we like, and the answer will not be the same. Okay, so we have to show that. So let epsilon be positive and let capital N be sufficiently large such that the following happen. Norm of yn minus y should be less than epsilon. Norm of yn dash minus y dash should be less than epsilon, and sigma I equals n plus 1 to infinity mod x ei square should be less than epsilon square for all n greater than equal to capital. Okay, now this is possible. Yn converges to y, and therefore for n sufficiently large. Yn dash converges to y dash, so again for n sufficiently large, so you have to take the bigger of the two. And then sigma mod xn square is a convergent series, so you know xei square, so we have it here, and therefore you could always find an n such that the tail of the convergent series can be made as small as you can. So we can find such an n. So now fix n greater or equal to capital N. Now if you take, then we can find m greater or equal to capital N such that the set E1 to En is covered by E1 dash to Em dash. So the n vectors here, I am finding a bigger set because this is a finite set and this is nothing but a renumbering of the same set, and therefore if I go far enough I should be able to cover all of them. Okay. Now you look at ym dash minus yn. So this will be of the form yn will be sigma I equals 1 to n x ei. Ym dash will be sigma I equals 1 to m x ei dash. But all the ei's are also contained in this sum, so they will all get cancelled. So what is remaining I am writing in terms of the ei's, where I is bigger than n. I is bigger than small n, sorry. and that of course is greater than capital N. So what do you get for ym dash minus yn square? Is equal to sigma x ei square. This is less than or equal to I equals n plus 1 to infinity, and that is less than epsilon square. Therefore, norm of y dash minus y is less than or equal to mod norm of y dash minus ym plus norm of ym y dash minus ym dash minus yn plus norm yn minus y. The first one is anyway less than epsilon. The second one we just saw is less than epsilon, and the third one is also less than epsilon, and therefore this is less than or equal to 3 epsilon, which is arbitrarily small, and this implies that y dash is the same as 1. So summary. So let S equals x set of all I in I such that xei is non-zero. Then you set E to be equal to E1, En and so on, numbering of S. So this is a countable set at most. Okay, and then you define sigma xei, I equals 1 to infinity, I in n as the as sigma I equal 1 to infinity x ei. I think let me put j, okay, where and this is from E, and this is equal to limit as n tends to infinity sigma j equals 1 to n xej. So this is, and it doesn't matter how you numbered the elements in E, and therefore you always get the same vector and so on. Now corollary, immediate corollary, that you have that x minus sigma I in I x ei is orthogonal to ej for all j in I. Okay.